In this video, we're going to explore cubic functions, the reverse engineering of those functions. That is to say, we're given either its parabola or its linear function, which is the second derivative, and we have to end up with the cubic function. So we're going to tackle the use of the derivative functions to deduce and sketch the corresponding cubic function. We're basically reverse engineering the cubic function based on a couple of aspects. If f of x is increasing, the original cubic function is increasing, then its parabolic function, f prime x, would have been smiling, or it would have a positive coefficient for x squared. And its f double prime, which is the second derivative, would have had a positive gradient. Conversely, if it was a decreasing function, the cubic function, then the parabola was going to be frowning or sad, and the second derivative, which is a linear function, was going to have a negative gradient. The x-intercepts of f prime correspond to the stationary points of f of x. The turning point of f prime, the parabola, corresponds to the point of inflection. It is also the axis of symmetry of the parabola, and you get that by adding the x-coordinate of one and to the other and divide by 2. The point of inflection is also the x-intercept of the second derivative, since at this point f double prime is equal to 0. How do we frame this concept? This concept is best framed by looking at exam type questions. The first question that we're going to look at is coming from November 2011. What we're given there was the parabola, and this parabola had an x-intercept at -4, another one at 1. And it was a frowning function. And -4 at this point. The graph of y prime, where f is a cubic function, is sketched. Use the graph to answer the questions that follow. For which values of x? For which values of x is the graph of y is equals to y prime decreasing? Decreasing means the function was going down. Then this is happening around the turning point of the graph. So we have -4, the first x-intercept. We add it to 1, the second intercept. So x at maximum is equals to -4 plus 1 divided by 2. This is going to be -3 over 2, which is otherwise known as -1.5. So the function was turning at -1.5. And the function was increasing for x less than -1.5. This is increasing, but what do we mean increasing? This is otherwise known as concave up. Concave up. Where was it decreasing? In the converse sense, the function was decreasing from x equal to -1.5 up to infinity. Negative up to infinity, the function was decreasing for all those values. So this is for x greater than -1.5. Another way of saying exactly the same thing is to say, where is the function concave down? Where is the function concave down? That answers the first part. They specifically wanted where the function is decreasing. The answer to that question is here. This is 1.1. This is just an extension, and I gave you in another way. They might ask, where is it increasing? Or more specifically, especially in this syllabus, they're more likely to ask concave up rather than increasing or decreasing. At which value of x does the graph have a local minimum? Give your answer. Give reasons for your answer. At which value of x does the graph f the original cubic function. The original cubic function. Where does it have a local minimum? Give reasons for your answer. To answer that question successfully, you need to have an appreciation of the connection between the parabola and its cubic function. This tells you that originally the coefficient was negative. And this was the first stationary point, and this was the second stationary point of the original f of x. So because it's a frowning function, then that means the original graph of f was like this. The original graph of f had that shape. In this case, its a would also have been negative. Since a is negative in this graph, then a is also going to be negative in this graph. And if a, which determines the shape of the function, is of this nature, then that means the first stationary point on this graph, the -4, that corresponded to a minimum. So the minimum was at -4, and the maximum would correspond to 1. So now let's answer the question. At which value of x, either -4 or 1, does the graph of f, the original cubic function, have a local minimum? Give reasons for your answer. 1.2 at x is equals to -4. And the reason for such is because the shape of f of x, the cubic function, was decreasing. By decreasing, I mean it would have looked like this. So it would have started at a minimum, which corresponds to the first stationary point, -4. Then it will proceed to a maximum, which corresponds to 1. What was required in this question was an intrinsic understanding of the relationship between the parabola, which was f prime, and its actual function, which is f. So you have to have an understanding of how these two functions are linked. That's how you can successfully navigate this question. That is the first example. Let's proceed to the second example. The question says, for a certain function f, the derivative is given as that. For a certain cubic function f. So we have an unknown cubic function, which I'll just call it according to its standard form, which is ax cubed plus bx squared plus cx plus d. We are given its first derivative. Its first derivative is f prime x. In this case, it's given as negative 3x squared plus 6x. That is the derivative of the unknown cubic function. And then we're given a corresponding graph. This is the graph f prime. It's crossing at 0. At this point, it's unknown. You take time to analyze and relate the graph to its equation. The negative signifies that it was a smiling or sad, it was a frowning or sad function. That's why the parabola is upside down. It's because of this negative. Then if we know one of them is 0, then we can easily figure out the second one by factorization. This is minus 3x, then x minus 2. Therefore, if it was equal to 0, that means x was equal to 0 and x was equal to 2. This corresponds to 2. This corresponds to the first stationary point on the graph of f, and this would correspond to the second stationary point. Calculate the x-coordinate of the stationary points of f of x. We have just done that. And all I had to do was take the first derivative, equate it to 0, and I would get two values. X is equals to 0, which was obvious, and x is equals to 2, which was less obvious because it was not stated. So what is key? How do you get all 3 marks? The derivative was given. You have to relate the phrase stationary points to f prime x. That recognition there. Then you equate it to 0. then you get the solutions. That link of the word stationary points to f prime x. Once you know the stationary points of f prime x of f of x can be got from f prime x, because the derivative at those two stationary points, the gradient is going to be equal to 0. Then you solve for the corresponding x values. So that first part answers question 9.1.1. Next question, determine the values at the point where the concavity of f of x, concavity, that phrase, concavity implies f double prime equal to 0, the point of inflection. So concavity simply means point of inflection. This is the point where the gradient changes. It's the point where the gradient changes. And how do we get this point of inflection? Well, this is the one point. This is the one way. F double prime of x equal to 0. That is the most obvious way. Or you can, here they wanted the x value. You can take the x at the minimum, add it to the x at the maximum, and divide those two. This is equal to the x at the POI, point of inflection. Why? Because the point of inflection is also the midpoint between the maximum and the minimum. Using that concept, this one, if we use this one, we're going to just be able to add those two and divide by 2, and we're going to get a corresponding 1. So the point of inflection has an x coordinate that corresponds to 1. How else could we have done it? We could have used calculus and just differentiated this another one more time, and we would get f double prime of x is equals to minus 6x plus 6. Then you equate that to 0, minus 6x plus 6. This is 6x is equals to 6x will be equal to 1. Two different ways we converge on exactly the same solution. So that word concavity there, it's very, very important that you are able to relate it to the second derivative equal to 0 and the midpoint, the point of inflection, which is the midpoint between the local minimum and the local maximum. That is key. It is further given that f of x is negative a x cubed plus b x squared plus cx minus 4, where f of 2 is 0. Draw a rough sketch of f of x. Clearly show the coordinates of the turning points. Okay, with this one, you need to use all the skills of analysis that you can master. What is important here? We are given the y-intercept. And then they also gave us f of 2 equal to 0. This is very important because it goes back to the tenets of algebra that are there in cubic functions. What tenets? This is to say where x is equals to 2, if we substitute f of 2, we get 0. This means we're using the factor theorem. We're using the factor theorem. So that means x is equals to 2 was a factor, is a factor. That is the first aspect. But if x is equals to 2, that means we have a point where there is 2 for x and 0 for y. This point is otherwise known as an X-intercept. This point is otherwise known as an X-intercept. Ironically, we have already seen this point before. We have seen it as a stationary point. So the point x is equals to 2 appears in two different ways. It appears as an X-intercept. It also appears as a stationary point. That means it is a repeated route. What do we link a repeated route to? The graph turns at that point. The graph would turn at that point. So if I were to sketch the corresponding function, the corresponding cubic function, not just any function, corresponding cubic function, I would have the point 2, then the other point was 0. Those are the stationary points of this graph. Those are the stationary points of this graph, but we are told D is minus 4. So this graph is going to turn at minus 4. It's going to turn because at 0 and minus 4, it is two things. It is it is also the stationary point, and minus 4 corresponds to the y-intercept. And then the parabola had a negative or a decreasing shape or a frowning, sad shape. That means the original function had exactly the same. So if I were to sketch it, it would have looked like this. Then it comes and turns at 2, going down. This is the corresponding function of f, using all the information that we know. To turn at 0 and minus 4, it's also having a y-intercept at minus 4. Then it's going to have an x-intercept as well as a turning point at 2. And lastly, its shape had to be a decreasing function. Again, you're linking the concepts. You are linking f of x to f prime x. The next question. The sketch below gives the graph of y prime of x. The sketch below gives the graph of y prime of x, and it looks like a parabola that is sitting right at the origin. A parabola that is sitting right at the origin. The original function f is obviously cubic. Write down the x-coordinates of the stationary points of f. Write down the x-coordinates of the stationary points or point of f. They're just equal to 0. X is equals to 0. Why? Because stationary points are equal to x-intercept of f prime x. The stationary points are equal to the x-intercept of f prime x. Well, this is a repeated root. X is equals to 2, x is equals to 0 twice. X is equals to 0 twice. And this x is equals to 0 is actually the stationary points of f because it was the x-intercept of f prime. So here, it's just x is equals to 0 twice. For which values of x, for which value or values of x is f decreasing? For which values of x or value or values of x is f of x decreasing? If this is the graph, then that means the graph was like that. Okay, let me draw it accurately. Negative, so it will start from above going below. And it's decreasing. For which value or values of x is f of x decreasing? If it is decreasing, its gradient is equals to 0. It's x greater than 0. It's x greater than 0. On this side, the gradient is negative. The graph is going down there. So it's decreasing on that side. We are using f prime x, the link. And the red graph that I've drawn there is just f. 9.1.3, it is further given that f of 0 is minus 5. F of minus 2 is 0. Draw a sketch of f in your graph. Draw a sketch of f in your graph. Now let me draw it accurately as possible, given those two pieces of information. Let's look at the first piece of information. The first piece of information we're given is f of 0 is equal to minus 5. This implies that x was equal to 0, and the corresponding value would be y is equal to minus 5. So there's a point 0 and minus 5. This point is otherwise known as the y-intercept. This point is otherwise known as the y-intercept. Secondly, we're given the point f of minus 2 is equal to 0. This means there is an x value that is equal to minus 2 and its corresponding y value is equal to 0. Therefore, there is a point minus 2 for x and 0 for y. Whenever y is 0, that implies that this is the x-intercept. This is the x-intercept. The last aspect we need to give a sketch of the graph is the shape, because f prime x is a said function. Said simply means it's upside down parabola. Then that means f of x is going to be a function of this type. It's going to be a function of that type. Combining all that information, we'll be able to get a sketch. And at x is equal to minus 2, this is f. And it is crossing at minus 5. So this is f of x, the original cubic function. We combined all that information. We were told the y-intercept, we were told the x-intercept, we deduced the shape, then you draw it as accurately as you can. Next question. The graph of h of x is equals to ax cubed plus px. We're given a graph of h of x is equals to ax cubed plus px. We are given a point on that graph which is 3 for x and minus 2 for y. The gradient of the tangent to h at the origin is 3. The gradient of the tangent at the origin where x is 0, y is 0 is just 3. So, h of x is given ax cubed plus px. It passes through the point 3 and minus 2. The gradient of the tangent. Gradient means we would have differentiated h prime x to give 3ax squared plus p. The gradient of this, if x was replaced with 0, was equal to 3. Therefore, 3a multiplied by 0 plus p is equal to 3. Therefore, p is equal to 3. That solves the aspect of p. Now we need to solve for a. Y is equals to ax cubed plus 3x. At this point, we only have one unknown. That unknown is a, which is the factor that gives us the shape. We substitute this point. This is our x, this is our y. Minus 2 is equals to a 3 cubed plus 3 times 3, because x is 3. So wherever there is x, we put 3. This is minus 2 is equals to 27a plus 9. transpose, we're going to get minus 11 is equal to 27a. Therefore, a is equals to minus 11 over 27. We got both of a and p. How did we do that? Well, we were given a function, h of x is equals to ax cubed plus px. And then if we substitute the point, we're going to have a simultaneous equation with two variables, a and p. Then we need more information, because to solve two unknowns, we need two equations. The second piece of information, the gradient of the tangent to h of x. The word gradient there in a context of calculus simply means differentiate, which is why I did this. So you take the original h of x function, you differentiate it once, you get 3ax squared plus p. Then they're saying the gradient to the tangent of this at h, you concentrate on the value of x. The value of x, because we need to substitute it into h prime x. So substituting the value of x, which is 0, which is why I said h prime of 0, and we were told the corresponding gradient is 3. So h prime of 0 is equals to 3. You come back to h prime x, the function, wherever there is x, you substitute 0. That's why I'm saying 3a times 0, it was actually 0 squared. Anything multiplied by 0 becomes 0. That leaves p, because p does not have any x, and p corresponds to 3. Once we know that p is equals to 3, we rewrite the equation. Y is equals to ax cubed plus 3x in place of p. Now we need another point. That's when we apply the point x is equals to 3 and y is equals to minus 2. If we substitute that, we're able to solve. A is equals to a negative 11 over 27. Lastly, determine the gradient of the tangent to h at x is equals to 3. The gradient. They want the gradient, then we have h of x is equals to minus 11 over 27 x cubed plus 3x. We differentiate once, h prime of x is equals to minus 33 over 27 x squared plus 3. We simplify that further, h prime of x is equals to 3 into that is minus 11, 3 into 27 is 9, x squared plus 3. I merely put that fraction in its lowest terms. Then we substitute the corresponding value of x, which is 3, is equals to minus 11 over 9, 3 squared plus 3. This is equals to minus 11 over 9 multiplied by 9 plus 3. This is minus 11 plus 3. Therefore, the corresponding gradient is equals to minus 8. The corresponding gradient is equal to minus 8. The next question. In the diagram, the graph of y is equals to f prime x is given. And this is corresponding to an f of x that is equal to a x cubed plus bx squared plus cx. Then we are given the y prime of x. It represents a cubic function. It is shown that f of 1 is equal to 0, as well as f prime of 2 is also equal to 0. Then f prime of 0 equal to 12. In our analysis, we said this simply means that the gradient at x is equals to 1 is 0. Gradient equal to 0. Then at x is equals to 2, the gradient is equal to 0. Then when x is equals to 0, the y-intercept is equals to 12. X is equals to 0, the corresponding y-intercept is equal to 12, and we can see that. Show that the equation of f prime x is equals to that. Show that the equation of that is equals to that in its x-intercept format. So what do? We've got two x-intercepts. F prime of x is equals to a, x minus 1, x minus 2. Now we need one more point to be able to solve for a. We'll substitute the point 12 and 0. So 12 is equal to a, 0 minus 1, 0 minus 2. Then we're going to have 12 is equal to 2a. Therefore, a is indeed 6. Therefore, f prime in its x-intercept format is 6, x minus 1, x minus 2 as required. Determine the x values of the stationary points of f of x. The x values of the stationary points, it's where I was saying the gradient is equals to 0. The gradient is equals to 0, then the stationary points at stationary points, gradient equal to 0. Therefore, x is equals to 1 and x is equals to 2. Those are the two x values that correspond to the stationary points. How do we know? Because at those corresponding points, f prime x is equal to 0. We saw this at 1, we saw this at 2. So that answers the question. X is equals to 1 and x is equals to 2. The values of x for which f of x is increasing. The values of x for which f of x is increasing. The corresponding value of function of f would have been like this. This was going to happen at 1, and this was going to happen at 2. It was going to turn at a local maximum at x is equals to 1, turn at a local minimum when x is equals to 2. Therefore, where is it increasing? When x is less than 1 and when x is greater than 2. Now, lastly, they want the equation of f of x. They want the equation of f of x. Let's combine all this information. We were told f of x is equals to a x cubed plus bx squared plus cx. That means d was 0, therefore d is equals to 0. If d is equals to 0, that is both its x-intercept as well as its y-intercept. So y was equal to x, then ax squared plus bx squared. Sorry, bx plus c. Then we have three unknowns. The first one we use y. We use the point x is equals to 1 and x is equal to 2. And the other point here, where f prime of 0 is equals to 12, when you differentiate this, f prime of x is equals to 3ax squared plus bx plus c. So c corresponds to 12. C corresponds to 12 because that is the y-intercept. C was 12. We can see it from there. Then we had the equation f prime x was equal to 6x minus 1, x minus 2. If you expand that, we're going to get 6x squared minus 3x plus 2. This is equals to 6x squared minus 18x plus 12. We already proved that c was 12. So the first aspect, this aspect of 3a squared coming from the original graph, is equated to this one. So 3ax squared is equals to 6x squared. The x squareds divide both sides. 3a is equals to 6a is equals to 2. Next up, this is equated to that negative 18x. And we're going to say x should be equal to negative 18x. So divide the x's both sides. B is equals to minus 18. Finally, this implies f of x, the original function, its a was 2x cubed. B is negative 18x squared. And lastly, c was 12x. That is how you relate the two, and you get the equation of the original function f from these pieces of information. The last question I want to do is question 3 on that page there. We're given g of x is equals to ax cubed plus bx squared plus cx plus d. It is in its standard form. Determine the values of a, b, c, and d if we're given those three pieces of information. It's actually 4. The first one says f of 2 is equal to 0. This, because it's f, therefore x is equals to 2 and y is equals to 0. This is known as the x-intercept of the function. Whenever y is equals to 0, the corresponding x value is the x-intercept. The second one is f prime of 1 is equal to 0. This means when x is equals to 1, the gradient of the function is equal to 0. Therefore, this is a stationary point. We're given f double prime of minus 2 is equal to negative 17. It's equal to negative 17. All this tells us is that on the second derivative, there's a point minus 2 and minus 17. But what is it really telling us? It's telling us that after minus 2, after negative 2, x is equals to negative 2, the rate of change of the gradient is negative. Rate of change of gradient is negative. That will help us decide whether it's before or after a turning point. Lastly, they say f double prime of 2 is equals to a positive 7. This is just a point on that graph. So how do we combine all this information to be able to get that? The first one we have is the x-intercept. And we need to get, I'm going to take away all this analysis and differentiate the function once and then twice. And then we back substitute. So, g of x f of x is equals to ax cubed plus bx squared plus cx plus d. F prime of x is equals to 3a squared plus 2b x plus c. F double prime of x is equals to 6ax plus 2b. The first is to say 7, substituting this point. So let me write using 2 and 7 in F double prime. That means 7 is equals to 12a plus 2b. Equation number 1. Then using minus 2 and minus 17 in F double prime, then that means negative 17 is equal to negative 12a plus 2b. Equation number 2. If I add those two equations, equation number 1 plus equation number 2, 7 is equals to 12a plus b, 2b, then minus 17 minus 12a plus 2b. If you add these two, you're going to get negative 10. This eliminates a. The a is eliminated because it's 12a minus 12a. This leaves us with 4b. So b is equals to negative 5 over 2. Once I get b, I'm in a position to get a by merely substituting in one of those two. So using equation number 1, sub b. This is 7 is equals to 12 multiplied by minus 5 over 2 plus, 12a plus 2 times minus 5 over 2. This means 7 is equals to 12a minus 5. 12 is equals to 12a. A is equals to 1. Now I know b and a. Now I know b and a. Next up, I need to use f prime. F prime of this, I know b and a. I'll be able to get c. So I'm going to erase this to make space. That implies that 0, because f prime is equals to 0. This will give me 3. I know a is 1. X squared. X at that point is 1. So 1 squared. Plus 2, but b is minus 5 over 2 multiplied by x, which is still 1, plus c. 0 is equals to 3 minus 5 plus c. I make c the subject. C is just going to be 2. I now know a, b, and c. The only piece of information missing is d. And that is the last piece of information, which I substitute into the original function using all these that I have. I have a, b, and then c. So using this, y is equals to a, which is 1x cubed, plus b, which is minus 5 over 2x squared, plus c, which is 2x, plus an unknown d. I'm going to use this x-intercept. X-intercept simply means x is equals to 2, corresponding y was 0. So in place of y, 0, wherever there's x, I'm going to put 2 cubed, minus 5 over 2, 2 squared, plus 2 times 2, plus d. This is 8. This minus 10, plus 4, plus d. This forms 12 minus that 0 is equals to 2 plus d, and d is equals to minus 2. Therefore, f of x is 1x cubed minus 5 over 2x squared plus 2x plus minus 2d in place of d. That question where you are constantly solving for multiple simultaneous equations, it ends in you having to sketch. Given the values determined above, sketch the graphs of on the same set of axes. So on the same set of axes, I now have to sketch the graph. Y prime was going to be 3x squared minus 5x plus 2. Okay, cubic function. First point is at 2. So the graph, which is smiling, has got minus 2 here. And the other point is at 2. Turns and goes. This is f. Then the quadratic function, the parabola. This was at 1, the turning point. This one my graph should be shifted that way. Its first turning point was at 1, at 2/3, then the other one was at 1, then it was going to cut at 2. Then its y-intercept was at positive 2, so turns there, and continues. This is at 2/3. This turning point is happening at 1. This is the cubic function. The parabola is just going to smile across this. So I've superimposed those two. This is f, and this is f prime on top of each other. That concludes this section of relating the parabola to its cubic function and also to the linear function of the second derivative.